Welcome to Unit 2. So we've got through Unit 1, which is all about organic structure. Unit 2 is where we start to talk about organic reactions. And so now we're going to actually put these structures that we've been talking about and thinking about and working on together and see what happens when two organic molecules react with each other. So we're going to start with very broad idea of like what types of reactions do we see in organic chemistry, and we're going to split things into basically three categories with two kind of types of mechanisms that we might see. So um, we're going to split them up. We're going to talk about what fits things into each category. And then as we go forward, as we move through chapter 4, which is acids and bases, and we're going to look at acid-base substitution reactions. And we're going to get to chapter 6, which is alkene addition reactions. And so we're going to do substitutions. We're going to do additions. We're going to go back to substitutions and eliminations. And we'll get through all of this stuff. And each one is going to kind of get its own chapter. So this is the big overview today, the introduction to this idea of the different types of organic reactions, and then over the next whatever 6 or 7 weeks and up through the next couple of exams, we're going to dig into each one of these categories a little bit further. Okay, so here we go. Here's a table of all the reactions that we are going to see in this course. So if this all makes sense to you, then you are set to go for this course. Every reaction in organic will appear somewhere on this table, right? And we're not going to talk about all of them, of course, but we'll dive into most of these, right? The thing to recognize is that each type of reaction, so substitution reactions like this, where a sigma bond is broken and a sigma bond is made, a substitution reaction like that is always going to kind of have the same types of things happen, right? You're going to break a sigma bond on one molecule, you're going to make a sigma bond to replace it. And these kinds of things, atoms are transferred from one reaction to another. This is the kind of thing that we look for when we see substitution, because that tells us where the electrons are going, how the electrons are flowing, and all that other kind of stuff, right? Same thing with eliminations, same thing with additions, right? So if you have an addition reaction, there's only one or two different ways that an addition reaction can take place. So if we can identify that a certain reaction is an addition reaction, it's pretty easy to figure out from there how the electrons move. Okay, so we have two main types of reactions. We have acid-base and we have radical reactions, right? So acid base, this is going to be like 90 to 95% of the reactions in organic uh, in this class, right? Almost all of the reactions are going to fall under acid base. And this is when two electrons move together. So very similar to what we've been doing in resonance, right? Whenever we move electrons, we're moving either a lone pair, so two electrons, or we're breaking a pi bond to move two electrons that way. So in acid-base reactions, we're going to do both of those things, but we're also going to occasionally break sigma bonds as well, right? And so, but again, still always pairs of electrons moving together. The radical reactions, radicals get their own chapter. They're a very separate group from the acid-base reactions. The radical reactions, the biggest difference is that we move unpaired electrons around. So instead of moving two electrons at a time, we have a single electron that that is very reactive, and so the single electron will share and unshare and all those other kinds of things. The three types of reactions that can be either acid-base or radical are substitution reactions, where we make a sigma bond and break a sigma bond. And so those would go here. You can do that either through an acid-base mechanism or a radical mechanism. Elimination reactions, where we make a pi bond. This is the big one for elimination reactions. Right? If you see that your product has a pi bond and your starting materials don't, an elimination reaction has probably occurred. Addition reactions go the other way, right? If you break a pi bond, so if you start from a pi bond and your product doesn't have any pi bonds or is missing a pi bond compared to your starting material, you've probably undergone an addition reaction, right? And so, where was I going with this? Yeah, so depending on the bonds made and the bonds broken, what we're really looking for, the skill that we want to work on kind of this week and right away before we even get into what these reactions look like, the skill that we want to work on is identifying what bonds are made and what bonds are broken. And of course, to do that, you're going to need to use a lot of the material that you used in the structure chapter. You're going to need to recognize, oh, there's a hydrogen at this position, even though it's not shown, or oh, this pi bond is moving from this position to that position, and those kinds of things, right? So all of that is going to be useful for you when you start to categorize and classify reactions. Okay, so Let's talk really quickly about acid-base. If I can get this thing to work, there we go. Acid-base reactions, two electrons move together, like we said. Every acid-base reaction has at least two components, an acid and a base, of course, that's why they call it that. We give them different names because not all acids and bases are the same. So when we talk about Lewis acids and Lewis bases, instead we say electrophile for the acid and nucleophile for the base. Right? And so in most acid-base reactions, you're going to have, or in all acid-base reactions, you're going to have an electron acceptor, which is going to be something that's positively charged or neutral, right? Because if it's positively charged, it's easy for it to accept electrons and attract negative charge, right? The nucleophile is going to be the opposite. That will be the electron donor. This will be the thing that shares its electrons with other things. So think about in resonance structures, where did we start all of our resonance structures? We always started from a lone pair or a pi bond or something that has excess electrons, right? That's this category, nucleophile. So a lot of the nucleophiles we're going to find are going to be lone pairs, pi bonds, that kind of thing. Things that are negatively charged tend to be good electron donors. Again, they have excess electrons to share. Also, some neutral compounds are also good nucleophiles. So you can see if there's charge, it's pretty easy to sort these things. Positive things tend to be acids, negative things tend to be bases. Right? And so if the skill is that we're looking to develop is to identify the acid and the base, what we really have to worry about is those neutral compounds. If we look at a neutral compound, how do we know if that neutral compound is acidic or if it's basic? And that's going to be something that we definitely spend a fair amount of time looking at because that's the hard thing in this skill, right? Most reactions fall into this category. As we said, this is about 90 to 95% of the reactions in this course. All right, so as we go forward, identifying the acid and base is going to be the thing that I'm going to constantly be asking you about. Where does this reaction start? What does the base look like? Which compound is the base? Which is the acid? Which one's the nucleophile? Which one's the electrophile? Expect to hear those questions from me pretty consistently going forward. The radical reaction. Radical reactions involve unpaired electrons, and these unpaired electrons combine and separate to form new bonds. Right? The identifying feature of a radical reaction is kind of two things that happen. There's an initiator, which is usually heat or light. Now, this is a hard one because it's not always heat or light doesn't necessarily indicate that a radical reaction is taking place. You can do acid-base reactions with high heat, right? So having heat in your reaction doesn't necessarily mean that it's radical, but it can be an indicator if there's also a homolysis reaction that's taking place. So if you have an initiator and there's homolysis occurring, then we're talking a radical reaction, right? Okay, so what is homolysis? Homolysis is a bond broken such that each atom of the bond receives one electron. Okay, so that makes sense. We're going to split, in this case, we're going to split this nitrogen-bromine bond, and one electron is going to go to the bromine, and one electron is going to go to the nitrogen, right? That's homolysis. The way that we know that it's the nitrogen-bromine bond is that bonds between heteroatoms tend to be weaker, right? So real quick, remember what a heteroatom is. Heteroatoms are atoms that are not carbon and are not hydrogen, right? So any atom that's not a carbon, not a hydrogen, that's a heteroatom. If you attach two heteroatoms together, they tend to have weaker bonds. So in this case, nitrogen and bromine are two heteroatoms. They have a weak bond, sigma bond between them. And so when we heat this up, that bond fragments. And it fragments by homolysis, right? So weak heteroatom bonds plus heat and light means that we have homolysis and an initiator. And so that means that this can be a radical process. So in this case, what we're looking at is we have this reaction where we go from this alkene starting material to a brominated product, right? And so it's pretty clear that what's been added, right? So what bonds have been made, right? Most of these bonds were present in the starting material, except for that bromine carbon bond, right? This carbon bromine bond, okay, we can highlight that. This carbon-bromine bond is one that was made over the course of the reaction. Because it wasn't here at the beginning, it is here in the product. Now it's a sigma bond, and that's important, right? Because we want to be able to go back to our table and look at that. So this is a sigma bond, the CBr sigma bond. now we need to figure out what bonds have been broken. So to do that, we look at the starting material and look at what atoms are no longer present in our product, or what bonds are no longer present. I shouldn't say atoms, but what bonds are no longer present. And we look at this, and there's a lot of similarity, right? We have a methyl group, we have an alkene, we have a methyl group, and an alkene. So a lot of those bonds are still present. So none of those bonds have been broken. So what bond has been broken? It turns out that in this case, the answer is this CH bond that's not drawn in, right? So we don't draw in CH bonds usually when we're drawing organic molecules just because there's so many of them. But sometimes they can be the bond that's broken when we do these reactions. And so fortunately, you guys have been practicing kind of identifying where are those CH bonds, recognizing that every carbon has to have 4 bonds, all that good stuff. And so when we see this bromine becoming attached to this carbon, we know that there used to be a hydrogen there. Now in the product, there isn't a hydrogen anymore because this carbon already has all 4 bonds to it, and so it's already shown, and we don't want to draw 5 bonds to carbon because that is not allowed. And so the only reasonable option is that the CH sigma bond was broken over the course of this reaction. And so we've broken a sigma bond and we've made a sigma bond. And so what type of reaction would this be if we go back to our table? Well, first of all, we know this is a radical reaction, and not just because it's on a slide that has radical at the top, also because we see that we have both an initiator and homolysis occurring. This is a radical reaction, but it's also a substitution reaction, right? So if we go back to our table here, right? Bond broken, sigma bond, bond made, sigma bond, that's a substitution reaction. And so this reaction that was on the radical page would fit into this part of the table where it's a radical process, but it's also a substitution reaction. And this is how we think about these types of bonds or these types of reactions. We look at what is the thing that's being made, what is the thing that's being broken. How do we make that new bond? Well, we have to break something in order to make something, right? Every reaction is going to have bonds made and bonds broken. And you're never going to have a reaction that only has bonds made and it doesn't have any bonds broken. I think that's true. I can't think of any examples, at least. There might be one out there. But so we always want to catalog what bond has been made, what bond has been broken. Right? And once we do that, then we can figure out, okay, if I'm making 2 sigma bonds and I'm breaking this pi bond, what type of reaction is that? Well, that's an addition reaction. Okay, so now I go to my addition reaction, whatever, mental folder or whatever, my list of addition reactions that can occur. And I think about how do the electrons move to make that addition reaction occur. And right now, you don't have that information because we haven't got to chapter 6 yet. But once we get through chapter 6, you're going to have a big long list of addition reactions that you're going to recognize, that you're going to be able to categorize even further into, okay, this is an addition reaction with a carbocation. This is an addition reaction that undergoes syn or syn addition, right? Or whatever all the terminology is. And so that's what we're going to work on. Is now we're going to drill down into each one of those little pieces of the table and say, well, what types of reactions occur in this corner of the table? What types of reactions occur in this corner of the table? And how do we kind of make sense of all of that? So that's where we're going. If you look through the reaction slides, I'm going to switch back there really quick, but if you look through the reaction slides, the last part of the reaction slides is an exercise for you to do. I have listed out 9 different reactions, and you can kind of sort them into, okay, this is an acid-base reaction, it's a substitution, acid-base substitution. This is a radical reaction, and it's an addition reaction. This one goes in that position, right? So we've already done one of them because it was on this page, but you can see, no, you can't. Now you can see, here's 9 reactions. There's a table here. You can kind of sort them in there. And then I also have the answer key and just kind of collections of all the substitution reactions together, all the addition reactions together, all the elimination reactions together. So do that. Make sure that this kind of thing makes sense. Find the ones that don't make sense to you and then bring those questions to me, either that or to your study group or whatever, right? To whoever you trust to answer your questions about organic chemistry. So that's the goal. That's the first thing that we're going to do in Unit 2. Next up, we're going to look at acid-base substitution reactions, in particular when we transfer a hydrogen from one to the other. And so that's going to be the next set of videos is going to be acid-base reactions. So I'll see you there. Let me know how this goes.